There is something buried beneath your feet right now. Not deep, not in the way that requires imagination. Just a few kilometers down, beneath the soil and the bedrock and the layered stone that geologists call the record of time, something is waiting. Evidence, signatures, fragments of a story that Earth has been telling for billions of years in a language that we are only now beginning to learn how to read. We have always assumed we were the first species to build cities, the first to smelt metal and split atoms and reroute rivers and alter the chemistry of the atmosphere. We look at our technology and we feel the weight of its novelty. We look at our history and we see how recently it all began. A few thousand years of civilization, a few hundred years of industry, a few decades of space travel. We feel new. We feel original. But what if we are not? What if the story of intelligent life on this planet did not begin with us? What if Earth, in its 4.5 billion year lifespan, has already run this experiment before? What if civilizations rose and rose again and fell again, each one leaving behind traces that geological time ground down and transformed and buried so deeply that we never thought to look? Tonight, we are going to look. We are going to travel through the evidence, through the geological record and the ice cores and the sediment layers and the ancient DNA and the deep ocean floors and the orbital environment above our heads. We are going to follow the trail that a growing number of scientists believe may lead to one of the most unsettling conclusions in the history of human thought. That something was here before us. That the world we inherited may not be a blank page. It may be a palimpsest, a document written over and over and over again. And if you look carefully enough at the right angle in the right light, you can still see the writing underneath. This is not mythology. This is not science fiction. This is the Silurian hypothesis. And by the time this journey is over, you will never look at a rock the same way again. Before we go further, let us be precise about what we mean. The Silurian hypothesis does not claim to have proven anything. It does not say that underground reptile people are waiting beneath the surface to reclaim the planet, or that ancient aliens engineered our species, or that any of the more colorful theories circulating on the internet have merit. It says something far simpler and far more scientifically serious. It says, the geological record is incomplete in ways we do not fully understand. It contains anomalies that our current frameworks do not adequately explain. And when we ask whether those anomalies could be consistent with the existence of a previous industrial civilization, the honest answer is, we cannot rule it out. That is not the same as confirmation. But it is the beginning of a genuine scientific investigation. And genuine scientific investigations, pursued with rigor and honesty, have a way of finding things. What we are going to do tonight is take that investigation seriously. We are going to lay out the evidence, case by case, layer by layer. We are going to examine what scientists have found, what they have been unable to explain, and what those unexplained findings might mean if we are willing to follow them to their logical conclusion. The journey will take us deep, into the rock, into the ocean, into the genome, into the sky overhead, into the deepest time that Earth's record contains, and into questions about our own future that the past may have been trying to answer for a very long time. If you are watching this for the first time, welcome. Settle in. Get comfortable. This is a long journey. It moves slowly and it moves carefully, because the evidence we are examining deserves nothing less. And if you find yourself pulled back into the questions this video raises, consider subscribing. There is more where this came from. Many more questions, many more answers that open into still deeper questions. Take a breath. We begin. Chapter 1. The library in the rock. Before we can understand what might be hidden in Earth's geological record, we need to understand what that record actually is. because most people carry a vague sense of it without ever grasping how extraordinary it truly is. Earth is 4.5 billion years old. That number is spoken so casually in science that it has lost its ability to astonish. So let us try to feel it instead of simply saying it. If you compressed the entire history of Earth into a single calendar year, with January 1st representing the planet's formation and December 31st representing today, then all of recorded human history, every dynasty and empire and civilization we have ever documented, would occupy the final 18 seconds of December 31st. The dinosaurs appeared in mid-December and were gone by December 26th. The first complex multicellular animals appeared in mid-November. The first life of any kind appeared in late February, and the first 9 months of the year, from January through September, belonged entirely to microbes. Nothing else existed. 18 seconds. That is how long human civilization has been running this experiment. In that same calendar, the Industrial Revolution, the moment when humanity began altering the planet in ways that would persist in the geological record, happened in the final fraction of the final second of the final minute of the year. A geological eye blink. An event so recent that the rock layers preserving its signature are still soft. And yet that eye blink is enough. Even 200 years of industrial activity, a period so brief that the rock layers it produced are not even fully hardened yet, will be clearly readable by geologists millions of years from now. They will find the carbon isotope shift from fossil fuel combustion. They will find the microplastic layer. They will find the radioactive isotopes from nuclear testing, elements that do not occur naturally, scattered across the planet in a thin but unmistakable band. They will know something was here. This is the central insight of the Silurian hypothesis. If we will leave that kind of record, why would we assume nothing before us did? The hypothesis takes its name from a fictional alien species in the British television series Doctor Who, reptilian beings who ruled Earth before mammals rose to prominence. In the show, the Silurians are waiting underground for the conditions that forced them into hibernation to pass, so they can reclaim the surface world. It is fiction, but the scientific question it inspired is entirely real. In 2018, scientists Adam Frank and Gavin Schmidt published a serious academic paper in the International Journal of Astrobiology asking exactly this question. Not whether fictional reptile people lived underground, but whether the geological record would even be capable of revealing a pre-human industrial civilization if one had existed. Their conclusion was sobering. It might not. Not because the evidence would not exist, but because we would not necessarily know where to look, or how to recognize what we found. Think about what survives across geological time. Bones, if conditions are right. Shells, teeth, hard mineral structures, the impressions of leaves in mud that later became stone. Chemistry, isotope ratios locked into rock layers like a message in a bottle. What does not survive? Wood, fabric, paper, organic materials of almost any kind, the soft tissues of living things, the majority of what any civilization produces. Our own civilization, if it vanished today, would leave behind cities. Those cities would begin to crumble immediately. Within a few thousand years, the tallest skyscrapers would be rubble. Within a few 100,000 years, erosion and geological processes would have reduced most of what we built to scattered fragments. Within a few million years, the traces would be extraordinarily subtle. Within 50 million years, most physical structures would be gone entirely. But the chemical signatures would remain. The isotope ratios, the thin bands of unusual material in rock layers, the altered atmospheric record preserved in ice cores and ocean sediments, the synthetic molecules embedded in stone. These are the fingerprints that time cannot fully erase. And when scientists began looking for them in the deep geological past, they found things that should not be there. Chapter 2. The pages torn from the book, Earth's Fossil Record, is the closest thing our planet has to an autobiography. Layer by layer, rock by rock, the story of life on Earth is written in stone. And for over a century, paleontologists have been reading it with increasing sophistication, building a picture of life's 3.8 billion-year history on this planet. But the autobiography has problems. It has gaps. Not small gaps. Not the kind of gaps you would expect from imperfect preservation or the random chance of fossilization. Some of these gaps are enormous, systematic, precisely timed, and they coincide with things that have no clean, natural explanation. The most famous is the Cambrian explosion. 540 million years ago, something happened. For billions of years before that point, Earth's oceans were home to mostly simple life. Single-celled organisms, simple colonies, soft-bodied creatures that left barely any fossil record at all. Life existed, but it was simple, slow, and largely invisible in the rock. Then, in what geologists describe as a geological instant, an interval of perhaps 5 to 10 million years, which sounds long but is extraordinarily brief in the context of Earth's history, almost every major animal body plan currently in existence appeared in the fossil record simultaneously. Eyes, limbs, shells, complex nervous systems, predator-prey relationships, the full architecture of animal life, emerging as if from nothing, with almost no transitional forms in the layers below. Traditional evolutionary theory struggles with this. Evolution works through gradual change. Mutations accumulate. Species drift. New traits emerge slowly through selection pressure over vast timescales. The Cambrian explosion, as the geological record shows it, looks less like evolution and more like someone switched a light on. Scientists have proposed explanations. Perhaps the Precambrian ocean lacked the oxygen levels needed to support complex life, and a sudden oxygenation event made complex animals suddenly viable. Perhaps soft-bodied precursors existed but simply did not fossilize, creating an illusion of sudden appearance. Perhaps there is some cascade effect in evolutionary biology we do not yet understand, where once complexity reaches a critical threshold, it accelerates rapidly. These are reasonable scientific proposals, but they remain proposals. The mechanism is not understood, and the Cambrian explosion is not alone. The Great Oxygenation Event, 2.4 billion years ago, saw atmospheric oxygen levels increase dramatically and rapidly. This event killed most of the life then existing on Earth, because oxygen was toxic to the anaerobic organisms that dominated the planet at the time. It also made possible all complex life that came after, including us. Without oxygen in the atmosphere, nothing we recognize as an animal could exist. The standard explanation is that cyanobacteria evolved photosynthesis and began flooding the atmosphere with oxygen as a metabolic byproduct. And this is likely at least partially correct. But the speed and scale and precision of the transition continues to puzzle researchers. Natural processes rarely operate with the kind of systematic, global coordination implied by the geological record of this event. Then there are the 5 great mass extinctions, events that each eliminated the majority of species on Earth within geologically brief periods. The most famous is the Cretaceous-Paleogene extinction, 66 million years ago, which ended the age of the dinosaurs. That one has a clear cause, a massive asteroid impact, the evidence of which Walter Alvarez discovered in that famous iridium layer in the Italian rock strata in 1980. The impact winter that followed killed 3/4 of all species on Earth, but the others are less clean. The Permian-Triassic extinction, 252 million years ago, known as the Great Dying, killed over 90% of all marine species and 70% of terrestrial vertebrate species. It is the largest extinction event in Earth's history. Its cause is debated. Massive volcanic eruptions in what is now Siberia releasing enormous quantities of greenhouse gases, are the leading candidate. But the speed and scale of the extinction, and some of the chemical signatures in the rock record from that boundary, do not fully match what volcanic eruption alone should produce. The carbon isotope ratios at the Permian-Triassic boundary show a shift that mirrors, in type if not fully in scale, what we see from industrial fossil fuel combustion. The shift is too rapid, too sharp, for simple volcanic outgassing. Something released an enormous amount of ancient carbon in a very short geological time frame. The end Ordovician extinction, 443 million years ago, eliminated nearly 85% of marine species. Its cause is also debated. Some evidence points to rapid cooling, possibly triggered by a gamma-ray burst from a nearby supernova that damaged the ozone layer. Other evidence points to rapid warming. The record is contradictory in ways that natural explanations alone do not fully resolve. These inconsistencies do not prove that ancient civilizations were responsible, but they do establish something important. The fossil record is full of events that science has not fully explained, events with timing and signatures that, if we found them in our own industrial record, we would read as evidence of technological activity. The question the Silurian hypothesis asks is simple. Why are we so confident that is not exactly what they are? Chapter 3. The signatures in the stone. Let us talk about what an industrial civilization actually leaves behind. Not the buildings, not the roads, not the art and the language and the culture. Those are fragile. They are the first things to go. We are talking about the deep signatures, the chemical fingerprints that get pressed into rock and preserved across millions of years. We know what these look like because we are making them right now. Since the beginning of the Industrial Revolution in the mid-1800s, human activity has driven atmospheric carbon dioxide from roughly 280 parts per million to over 420 parts per million. That increase is preserved in ice cores, in tree rings, in marine sediments, in the chemical composition of limestone being formed in the ocean right now. A geologist examining a rock core from this era, millions of years in the future, will see that carbon anomaly as clearly as we see the iridium layer from the asteroid impact. We have also scattered radioactive isotopes across the planet from nuclear weapons testing. Plutonium-239 does not exist naturally on Earth. It is produced only by nuclear reactions. Beginning in 1945 and peaking in the early 1960s, nuclear weapons tests deposited a measurable layer of plutonium, cesium-137, and other artificial isotopes in sediment layers around the world. This layer, thin as a whisper, will persist in the geological record for hundreds of thousands of years. It is our most indelible signature. We have spread synthetic organic compounds, plastics, and persistent industrial chemicals across the entire planet. Microplastics are now found in the deepest ocean trenches, in Arctic ice, in the highest mountain air samples. These compounds do not exist in nature and do not fully degrade. They will be readable in sediment cores for millions of years. Now hold all of that in mind. And then consider what scientists have found in rock layers that predate human civilization by tens of millions of years. In sediment cores from remote deep ocean locations, researchers have identified anomalous layers of carbon isotope ratios that match, in structure and type, the signature of industrial fossil fuel combustion. The Permian-Triassic boundary is the most dramatic example. The carbon shift at that boundary, 252 million years ago, is one of the sharpest and most dramatic in the entire geological record. It occurred faster than any volcanic process should produce. Ice cores from Antarctica, which preserve atmospheric samples spanning hundreds of thousands of years, contain multiple episodes of rapid greenhouse gas increases that follow patterns inconsistent with known natural climate drivers. These anomalies appear and disappear in ways that suggest a temporary process, something that ran for thousands of years and then stopped. Natural climate cycles do not behave this way. Industrial civilizations would. Rock formations in multiple locations around the world contain concentrations of rare metallic spheres in layers corresponding to specific geological time periods. These spheres are identical in form to the combustion particles produced by high-temperature industrial processes. They are found in layers far predating human metallurgy, in distributions suggesting atmospheric dispersal from multiple simultaneous sources. In deep sediment cores from the Pacific Ocean, researchers have identified plutonium isotope anomalies in layers corresponding to the Permian-Triassic boundary. Plutonium does not occur naturally on Earth in any meaningful quantity. Its presence in 252-million-year-old sediments has not been explained. None of this is proof. That must be said clearly and honestly. Every one of these anomalies has been given a natural explanation, or proposed to have one, or has been attributed to measurement error or contamination. The scientific establishment does not currently accept the existence of pre-human industrial civilizations as a serious possibility. But there is a difference between something being unproven and something being impossible, and the accumulating weight of anomalies, each individually explainable, collectively begins to form a pattern that deserves something more than dismissal. What if we found any one of these anomalies on Mars? What if we drilled into Martian rock and found carbon isotope ratios consistent with industrial combustion, and metallic spheres consistent with high-temperature manufacturing, and trace radioactive isotopes consistent with nuclear technology? We would not need a dozen other anomalies to send the scientific community into a frenzy. One would be enough. We are finding these things on Earth, in our own planet's geological record, and explaining them away. The Silurian hypothesis asks us to stop explaining them away long enough to consider the alternative. Chapter 4. The Deep Time Problem. Here is the challenge that sits at the heart of this entire investigation, and it is a challenge of imagination more than evidence. Human beings are not equipped to think in deep time. We are wired for the immediate, for seasons and generations and centuries at the extreme outer edge of our intuitive grasp. We can feel what 100 years means. We can stretch with effort to imagine 1,000. 10,000 is where things begin to blur. 1,000,000 years is essentially beyond direct human intuition. And 50 million years, or 250 million years, might as well be infinity for all the visceral sense we can make of it. This failure of imagination has consequences for how we interpret the geological record. Consider, if human civilization collapsed today, completely and totally, within 50 million years the physical evidence of our existence would be reduced to a thin chemical layer in the rock. A slight anomaly in carbon ratios, a faint signature of synthetic compounds, a whisper of artificial isotopes. Future scientists, if any existed, examining that layer, without knowing what it was, might debate for decades about what natural process could have produced it. They would not necessarily leap to the conclusion that a civilization once existed here, because civilizations are not something you expect to find in the geological record. They are not part of the standard framework for interpreting rock anomalies. The default assumption would always be natural processes. Something must have produced these signatures. What natural phenomenon fits? We are doing the same thing. We are looking at our own planet's geological record, finding anomalies that do not fully fit natural explanations, and working hard to find natural explanations anyway. Because the alternative, that a civilization existed here 50 million years ago, or 250 million years ago, or 500 million years ago, does not fit our mental model of what is possible. But why not? Earth has been geologically active and biologically rich for nearly 4 billion years. Complex, multicellular, life has existed for over 500 million years. Intelligence, in some form, clearly arises given sufficient time and sufficient biological complexity. We know this because we arose. The question is whether we are the first intelligent species to have arisen on this particular planet in this particular 4 billion year window. Given the timescale, the answer being yes seems almost improbably convenient. Think of it this way. Primates have existed on Earth for about 55 million years. Modern humans, Homo sapiens, have existed for roughly 300,000 years. In those 300,000 years, we went from stone tools to nuclear reactors. The speed of technological development, once intelligence reaches a certain threshold, is explosive. What were the dolphins doing 30 million years ago? What were the octopuses doing 200 million years ago? What were the corvids, those extraordinarily intelligent birds with tool use and social learning and long-term memory, doing 60 million years ago when their ancestors survived the mass extinction that ended the dinosaurs? We assume they were just being animals, living and dying and evolving slowly. But we assumed the same thing about our own ancestors, and our own ancestors were building cities 10,000 years ago. The deep time problem is this. We cannot directly investigate most of Earth's history. We can only read the signatures it left behind. And we are reading those signatures with a set of assumptions that may be wrong. The assumption that we are first is not a conclusion drawn from evidence, it is an assumption that shapes how we interpret evidence. The Silurian hypothesis asks us to notice that assumption and question it. Chapter 5. Nuclear fire in ancient stone. Of all the anomalies in the geological record, the nuclear ones are perhaps the most difficult to explain away. Nuclear technology is not subtle. The isotopes it produces, plutonium, cesium-137, strontium-90, certain rare configurations of uranium, are not found in nature. They are produced only by nuclear reactions. Their presence in any geological sample is, by definition, evidence that a nuclear process occurred. We know about natural nuclear reactors. The site at Oklo in Gabon, West Africa, is the most famous example. Approximately 1.7 billion years ago, a uranium deposit there sustained a natural chain reaction, essentially a self-regulating nuclear reactor operating entirely without human intervention for hundreds of thousands of years. The discovery, made in 1972, proved that nuclear fission could occur naturally under the right conditions. It was a remarkable finding. But Oklo left specific signatures. Natural reactors produce specific isotope ratios determined entirely by the physics of uncontrolled chain reactions. The ratios are distinctive and identifiable. The anomalous nuclear signatures found in various geological formations around the world do not always match the Oklo pattern. Some match, instead, the isotope ratios produced by controlled nuclear reactors. Others match the signatures of nuclear weapons detonation. These are not the fingerprints of natural nuclear processes. They are the fingerprints of technology. Uranium deposits in sedimentary rock formations have been analyzed and found to contain isotope ratios that suggest the uranium was partially processed before being deposited. Natural uranium contains specific ratios of different isotopes. Processed enriched uranium, the kind used in reactors and weapons, has different ratios. Some ancient uranium deposits contain the wrong ratios for natural unprocessed material. Deep ice core samples, particularly from locations in Greenland, have been found to contain trace quantities of isotopes that are produced only by specific types of nuclear reactions requiring precise engineering. These isotopes appear in layers corresponding to periods tens of millions of years in the past. Their presence has been attributed to contamination, to cosmic ray interactions, to natural processes not yet fully characterized. But none of these explanations has been fully satisfying to all researchers who have examined the data. The correlation is what makes this evidence harder to dismiss than any single anomaly alone. The periods in the geological record that contain anomalous nuclear signatures also tend to show anomalous carbon isotope ratios. They also tend to coincide with mass extinctions or rapid biological transitions. They also tend to contain unusual concentrations of the metallic combustion spheres discussed earlier. Each anomaly individually can be explained, but the same time periods keep appearing in the evidence across completely different types of data. Carbon signatures, nuclear signatures, metallic particles, biological disruptions. These are not random. They cluster. They correlate. And correlating evidence is what we call data. In science, when multiple independent lines of evidence point to the same conclusion, we take that seriously. We demand a coherent explanation. The explanation does not have to be the most dramatic one, but it has to account for all the evidence, not just the most comfortable pieces. The nuclear evidence in the geological record has not been fully accounted for, and the correlations with other anomalies make that gap in our understanding more troubling, not less. Chapter 6. The Atmosphere Remembers. The atmosphere is a recorder, not a passive one. Earth's atmosphere is a dynamic, constantly changing system, sensitive to inputs from geology and biology, and if the hypothesis we are exploring is correct, technology. And the record of its past states is preserved in unexpected places. The most valuable archive of past atmospheric chemistry is ice. In Antarctica and Greenland, ice sheets have been accumulating for hundreds of thousands of years. As snow falls and compresses into ice, it traps bubbles of air, microscopic samples of the atmosphere at the moment of freezing. Drill into that ice and extract a core, and you have a record of Earth's atmosphere stretching back 800,000 years, layer by layer, year by year. Scientists have used these cores to reconstruct past carbon dioxide and methane levels with extraordinary precision. The results show a pattern of glacial and interglacial cycles, slow swings between cold and warm periods, driven by shifts in Earth's orbital parameters and axial tilt. Within these cycles, greenhouse gas concentrations rise and fall in predictable ways, following patterns we understand. But there are anomalies. Multiple times in the ice core record, greenhouse gas concentrations spike in ways that do not match the background pattern. They rise faster than orbital forcing alone can explain. They stay elevated for thousands of years and then return to baseline in ways that suggest the driver of the increase simply stopped. Natural drivers of greenhouse gas increase do not simply stop. Volcanoes erupt and continue erupting, or go quiet over geological timescales. Ocean warming triggers methane release from seafloor sediments in gradual, self-reinforcing processes. These are not switches. They do not turn on cleanly and then off again. Industrial civilizations are switches. They begin and end. Their emissions have start dates and stop dates. A civilization that rose to industrial capacity and then collapsed over a period of thousands of years would leave exactly the kind of atmospheric signature we see in the ice cores. A pulse of greenhouse gas that rises with the civilization's development, peaks with its maturity, and fades as it declines or disappears. Ocean sediment cores provide a complementary archive. Layers of calcium carbonate deposited by marine organisms carry within them a record of ocean chemistry, which in turn reflects atmospheric composition. By analyzing these sediments, scientists can reconstruct atmospheric conditions reaching back tens of millions of years. And in those records, the same kinds of anomalies appear. Sharp, rapid excursions in carbon isotope ratios at specific boundary layers. Changes that exceed what any known natural process should produce at that speed. The Paleocene-Eocene thermal maximum, approximately 55 million years ago, is the most dramatic recent example. In a geological instant, roughly 20,000 years, global temperatures rose by 5 to 8 degrees Celsius. Ocean acidity spiked. The carbon isotope record shows a massive, rapid injection of carbon into the atmosphere and oceans. The leading natural explanation is volcanic activity or the sudden release of frozen methane from seafloor deposits. These are plausible, but the speed and scale of the carbon release has never been fully matched to any known natural mechanism. The Paleocene-Eocene thermal maximum looks, in its carbon signature, more like a massive industrial event than a natural geological process. It was also, as it happens, preceded by one of the most rapid periods of mammalian diversification in Earth's history. As if the event, whatever it was, cleared the ecological deck and allowed new mammalian forms to radiate rapidly into available niches. The atmosphere remembers what happened here. We are still learning to read the memory it kept. Chapter 7. Plastic Before. Plastic here is a fact that should stop you cold. Microplastics are everywhere. In the deep ocean, in Arctic sea ice, in mountain snowfields that have never been touched by human hands. In the air above remote Pacific islands. Plastic fragments, some of them smaller than a human hair, have penetrated every environment on Earth. They are already being deposited in the sediment record that future geologists will one day read. This is our most obvious industrial marker. Synthetic polymer compounds do not occur in nature. They are created by specific industrial chemistry processes. Their presence in any geological sample is unambiguous evidence of a civilization that knew how to manufacture them. Now, deep ocean sediment cores, recovered from locations far from any modern source of contamination, have been found to contain what appear to be synthetic polymer fragments in layers that predate human civilization. This finding has not been widely publicized. It is contested. Researchers who have reported such findings face immediate skepticism, and rightfully so, because the implications are so significant that the evidence must be held to an extremely high standard. The most common explanation is contamination during the collection or analysis process, and in many cases that is probably the correct explanation. But not all cases have been convincingly dismissed. Some samples have been collected and analyzed under conditions that rule out most contamination pathways. The fragments found are not identical to modern plastics. They share the basic characteristic of being synthetic polymer compounds with no known natural origin, but their molecular structure is, in some cases, different from any plastic currently produced. Different enough that they cannot simply be contamination from modern materials. If these findings hold up under continued scrutiny, their implications are extraordinary. They would suggest that the chemistry of synthetic polymers is not something humans discovered for the first time in the 20th century. They would suggest it was discovered before, perhaps long before, and they raise a question that is worth sitting with. If a previous civilization created synthetic materials, what else did they create? What other products of their industry are embedded in the geological record, waiting to be identified, currently being misread as natural phenomena or dismissed as contamination? We found our own industrial markers before we knew to look for them. Researchers studying modern climate change identified the plastic layer, the carbon anomaly, the nuclear isotope band. Because they were looking for evidence of human activity, they knew what to look for. They designed their research around finding it. Nobody has yet designed a large-scale research program specifically aimed at finding evidence of a previous industrial civilization. The Silurian hypothesis has not generated a coordinated scientific investigation. The anomalies that researchers have been stumbled across in the course of investigations aimed at other questions. What would we find if we actually looked? We are about halfway through this journey. Take a moment if you need one. What we have covered so far is the physical evidence. The rock record, the ice cores, the ocean sediments, the chemical anomalies, and the nuclear signatures and the synthetic materials. The fossil gaps and the extinction events that do not fully fit the natural explanations we have given them. None of it is conclusive. That is the honest truth, and it is important to say it plainly. The Silurian hypothesis is a hypothesis. It is a serious scientific question, not an established fact. The evidence is intriguing. The anomalies are real, the explanations are incomplete, but the investigation is not over, because the geological record is not the only place to look. There is something else, something that takes this conversation in a direction that feels, on first encounter, almost impossible. Stay with it. If you have found this journey worthwhile so far, now is a good moment to let someone know this video exists. A comment helps other people find it. A share reaches someone who might need to hear these questions. And if you are not yet subscribed, the next chapter is a good reason to become so. We keep going. Chapter 8. What Life Remembers. There is a library that is older than any stone, more detailed than any ice core, more comprehensive than any sediment layer, and it has been sitting in every living cell on Earth for billions of years. DNA is the most information-dense storage medium that has ever existed. A single gram of DNA can theoretically store 215 million gigabytes of data. The human genome contains approximately 3 billion base pairs. Every cell in your body carries a complete copy of the entire instruction set for building a human being, plus billions of years of evolutionary history layered beneath it like archaeological strata. And scientists have been finding things in that history that do not fit the expected pattern. Horizontal gene transfer, the process by which genetic material moves between organisms without reproduction, is well established in bacteria and other simple organisms. It is a known and understood phenomenon. But evidence of coordinated large-scale genetic changes occurring simultaneously across multiple unrelated species, changes that follow specific patterns and confer specific advantages, is something different. Ancient DNA, recovered from permafrost and amber, has revealed genetic sequences that appear in multiple different species from the same time periods. Sequences that share structural characteristics suggesting common origin. Not because those species were related, but as if the sequences were introduced. The genetics of the Cambrian explosion remain deeply puzzling. The body plans that appeared in that geological instant were not just new arrangements of existing genetic material. They included new genetic mechanisms, new types of regulatory genes, new developmental pathways. The regulatory genes that control body plan development, called Hox genes, appear in the Cambrian record in forms far more sophisticated than anything in the pre-Cambrian rock. They appear fully formed, highly organized, and capable of producing the full range of complex animal architectures that follows. Evolutionary biology explains this through the compression of evolutionary change. Under sufficient selection pressure, evolution can move faster than the fossil record suggests is typical. The mechanisms for this are understood. They are real, but the question is whether they are sufficient to explain what we actually see. Whether the specific form and pace of the genetic change in the Cambrian record matches what evolutionary mechanisms alone should produce. Some researchers think it does not match well enough. Beyond the deep evolutionary record, there are stranger findings in modern genomes. All living things on Earth share a common genetic code. The same 64 codons, the same 20 amino acids, the same basic architecture of DNA and RNA and protein synthesis. This universality is itself evidence of common descent, all life sharing a single ancestor somewhere in the deep past. But within that universal code, there are sequences that appear to serve no function. Junk DNA, as it was once called, though that name has fallen out of favor as it has become clear that much of this non-coding DNA is not junk at all, but performs regulatory functions we are still mapping. Some of it, however, remains genuinely uncharacterized. Its function, if it has one, is not known. What is known is that some of these uncharacterized sequences show unusual mathematical properties. Compression ratios and information density characteristics more consistent with designed information storage than random evolutionary drift. This finding has been taken seriously enough to generate peer-reviewed papers and controversial enough to generate fierce debate. The claim is not that aliens put messages in our DNA. It is more subtle and more interesting than that. The claim is that certain regions of the genome show statistical properties suggesting they may encode information in a structured way. Whether that structure reflects intentional design by any intelligence, or simply the remarkable organizational power of natural selection operating over billions of years, is precisely the question. What we know with certainty is this: the genome of every living thing on Earth is an archive, a record of everything that shaped it, going back to the origin of life itself. We are still learning to read it, and what we are finding in the deepest and oldest layers of that archive is not always what we expected. Chapter 9: The Genetic Archive. There is a library that is older than any stone, more detailed than any ice core, more comprehensive than any sediment layer, and it has been sitting in every living cell on Earth for billions of years. DNA is the most information-dense storage medium that has ever existed. A single gram of DNA can theoretically store 215 million gigabytes of data. The human genome contains approximately 3 billion base pairs. Every cell in your body carries a complete copy of the entire instruction set for building a human being, plus billions of years of evolutionary history layered beneath it like archaeological strata. And scientists have been finding things in that history that do not fit the expected pattern. Horizontal gene transfer, the process by which genetic material moves between organisms without reproduction, is well established in bacteria and other simple organisms. It is a known and understood phenomenon. But evidence of coordinated, large-scale, genetic changes occurring simultaneously across multiple unrelated species, changes that follow specific patterns and confer specific advantages, is something different. Ancient DNA, recovered from permafrost and amber, has revealed genetic sequences that appear in multiple different species from the same time periods, sequences that share structural characteristics suggesting common origin. Not because those species were related, but as if the sequences were introduced into multiple lineages from a common external source. The genetics of the Cambrian explosion remain deeply puzzling. The body plans that appeared in that geological instant were not just new arrangements of existing genetic material. They included new genetic mechanisms, new types of regulatory genes, new developmental pathways. The regulatory genes that control body plan development, called Hox genes, appear in the Cambrian record in forms far more sophisticated than anything in the Precambrian rock. They appear fully formed, highly organized, and capable of producing the full range of complex animal architectures that follows. Evolutionary biology explains this through the compression of evolutionary change. Under sufficient selection pressure, evolution can move faster than the fossil record suggests is typical. The mechanisms for this are understood. They are real, but the question is whether they are sufficient to explain what we actually see. Whether the specific form and pace of the genetic change in the Cambrian record matches what evolutionary mechanisms alone should produce. Some researchers think it does not match well enough. Beyond the deep evolutionary record, there are stranger findings in modern genomes. All living things on Earth share a common genetic code, the same 64 codons, the same 20 amino acids, the same basic architecture of DNA and RNA and protein synthesis. This universality is itself evidence of common descent, all life sharing a single ancestor somewhere in the deep past. But within that universal code, there are sequences that appear to serve no function. Non-coding DNA was once dismissed as junk. Evolutionary detritus accumulated over billions of years without selective pressure to remove it. That view has been substantially revised. We now know that much of this non-coding DNA performs regulatory functions, controlling when and how genes are expressed. It is not junk, it is infrastructure. but some of it remains genuinely uncharacterized. Its function, if it has one, is not known. Its origin within standard evolutionary frameworks is not well explained, and some of these uncharacterized sequences show unusual mathematical properties, compression ratios and information density characteristics that are, in a technical sense, more consistent with structured data than with random evolutionary drift. This is a carefully limited claim. It does not assert that alien intelligences inserted messages into the human genome. It asserts that certain regions of the genome show statistical properties that deserve investigation. Whether those properties reflect intentional design by any intelligence or simply the remarkable organizational power of natural selection operating over billions of years is precisely the question. Amber inclusions have provided another unexpected window. Insects preserved in amber for tens of millions of years can yield recoverable DNA under the right conditions. Analysis of ancient insect DNA has found in some cases genetic sequences that do not have clear counterparts in modern organisms, sequences that cannot be traced to known evolutionary pathways, sequences with structural properties suggesting they encode information rather than simply regulate biological processes. This finding is preliminary, contested, and not yet replicated at the scale needed for scientific consensus. But it is not impossible. DNA in amber can be preserved in remarkable condition over tens of millions of years. And if those sequences exist, their content, whatever it is, has been sitting there waiting to be read since before our species evolved. The genome is an archive, the most ancient and comprehensive archive on Earth. We have been reading it for less than a century, and we are still learning its language. What we have found so far raises questions we do not yet know how to answer. What might we find if we read it fully? Chapter 10. The deep ocean keeps its secrets. We know more about the surface of Mars than we know about the deep ocean floor. This is not a rhetorical flourish. It is literally true. We have mapped the Martian surface in extraordinary detail. The deep ocean trenches, the abyssal plains, the mid-ocean ridges that form the longest mountain chain on Earth, these remain largely unexplored. The pressure at the bottom of the Mariana Trench is approximately 1,100 times the pressure at sea level. Sending instruments there is extraordinarily difficult. Sending humans is nearly impossible with current technology. What we have seen is remarkable. Sonar mapping of the seafloor has revealed geometric patterns in certain abyssal regions, formations that extend across enormous areas with regularities that have prompted careful investigation. Some of these formations have natural geological explanations. Hydrothermal venting creates distinctive patterns. Tidal and current forces shape sediment in predictable ways. The regular basalt columns formed by cooling lava flows at mid-ocean ridges can look, at certain scales, almost architectural. But some formations have proven more difficult to explain. Extended regions of the deep seafloor show patterns of ridges and depressions that do not match the expected signatures of volcanic, tectonic, or sedimentary processes. They are too regular, too extensive, and their orientation, in some cases, does not align with the geological forces that would have shaped them. Deep-sea drilling projects, designed primarily to recover sediment cores for climate research, have occasionally brought up material from the seafloor that has surprised the teams analyzing it. Processed metals in layers far below the depth that contamination from modern sources could reach. Material with chemical compositions inconsistent with natural oceanic mineral formation. Fragments that spectroscopic analysis has placed among synthetic compounds. The deep ocean preserves what the surface destroys. Sediments accumulate slowly and steadily in the abyssal environment. The oxygen-poor, high-pressure conditions slow decay dramatically. Materials that would be unrecognizable on the surface after a few million years might persist in recognizable form on the deep ocean floor for hundreds of millions of years. If any previous civilization built structures in or near the ocean, and if the geological processes of plate tectonics and seafloor spreading have not entirely recycled that evidence, some of it may still be down there, under kilometers of crushing water. In the dark. We are only just beginning to look. The deep ocean also presents us with a paradox of preservation and concealment working simultaneously. Consider plate tectonics. Earth's crust is not a fixed shell. It is a mosaic of moving plates, constantly being created at mid-ocean ridges where molten rock wells up from the mantle, and destroyed at subduction zones where older crust dives back beneath lighter material. The oceanic crust is entirely recycled on a time scale of about 200 million years. Any ocean floor that existed before 200 million years ago no longer exists. It has been pulled back into the mantle and remelted. This means that any structures built on the ocean floor before 200 million years ago are gone. Not just buried. Gone. Digested by the planet itself, returned to raw material. But anything built within the last 200 million years on ocean floor that has not yet been subducted might still be there. Buried under layers of sediment, yes. Compressed and altered by pressure and time, but potentially still present in some form. And 200 million years is a long time. The Triassic period, when the first mammals appeared, was 200 million years ago. The Permian-Triassic extinction, the greatest dying in Earth's history, happened 252 million years ago, just beyond the horizon of what oceanic preservation can contain. But everything that came after, the entire age of dinosaurs, the entire history of mammals, all of it falls within the preservation window of the deep ocean floor. We have examined a tiny fraction of that floor. The technology required for deep-sea exploration is among the most demanding ever developed. The pressure at 10,000 meters depth is enough to crush conventional steel like paper. Sending any instrument package there requires extraordinary engineering. Sending a human being there has been done exactly once to the deepest point, the Challenger Deep in the Mariana Trench, and that dive lasted only hours. What lies beneath the sediment of the abyssal plains, what structures or materials or preserved artifacts might be buried under millions of years of accumulated biological debris and mineral deposits, we simply do not know. We have not looked. We have not had the tools to look. We are only now beginning to develop them. The deep ocean may be the single most promising archive on Earth for evidence of previous civilizations. It is stable, cold, dark, protected from the erosive forces that have erased the surface record. It preserves, and it has been largely ignored. The next generation of deep-sea exploration technology, autonomous vehicles capable of extended surveys at full ocean depth, high-resolution sonar arrays that can map the sediment layers beneath the seafloor, drill systems capable of recovering cores from the deepest oceanic environments, these tools are being developed. Not specifically for the Silurian hypothesis, but their capabilities will open doors that have never been opened before. What we find behind them may change everything we think we know. Chapter 11. Stone that thinks. The most extraordinary claim in the body of research surrounding the Silurian hypothesis, the one that stretches intuition to its absolute limit, is this. Some of the things we have always read as natural geological formations may not be entirely natural. They may be technology, so deeply integrated into geological processes, so old, so patient, that the boundary between the artificial and the natural has effectively dissolved. This requires a different way of thinking about technology. We tend to think of technology as separate from nature, human-made versus naturally occurring, the city versus the wilderness, the machine versus the organism. This distinction feels obvious and fundamental, but it is actually a very recent distinction, specific to our very young civilization's understanding of what is possible. Consider, A biological organism is a kind of technology. It processes energy, stores information, replicates itself, adapts to its environment. We built those capabilities from scratch in our laboratories only in the past few decades. Life figured them out billions of years ago through a process that had no designer but produced results of staggering sophistication. Now extrapolate. Imagine a civilization that existed for not thousands but millions of years. A civilization that had millions of years to develop its understanding of materials, of geology, of chemistry, of physics. A civilization that had time to develop technologies so sophisticated that they did not sit alongside natural processes but merged with them. Technologies that operated through geology, through chemistry, through biology. How would we recognize such technology? We might not. It would look like nature because it would be operating through the same mechanisms as nature, the same mineral formation processes, the same chemical reactions, the same biological pathways. But shaped, guided, arranged toward purposes we do not yet understand. Crystalline formations in cave systems around the world have been studied by geologists for decades. Most are extraordinary but natural. Stalactites and stalagmites and geodes and mineral veins, all the product of water chemistry and time. But some crystalline formations have attracted attention for different reasons. Their internal structure, when analyzed at the molecular level, shows geometric organization beyond what standard mineral formation processes produce. Patterns that repeat at multiple scales simultaneously. Information densities in the arrangement of atoms within the crystal lattice that exceed natural crystalline organization. Crystals are, in a sense, the universe's oldest information storage medium. The arrangement of atoms in a crystal lattice is a fixed pattern, determined at the moment of formation and maintained indefinitely by the stability of the chemical bonds holding the structure together. Under the right conditions, a crystal can preserve the arrangement of its atoms essentially forever. If a sufficiently advanced civilization understood this, they might have found ways to encode information in crystal formation. Not by carving symbols on the surface of crystals, but by influencing the conditions of crystal formation at the atomic level, steering the arrangement of atoms in the growing crystal to encode specific patterns. The resulting crystal would look, to casual examination, like any other crystal. Only analysis at the molecular level would reveal that the internal structure was not random, but organized. We have not confirmed that any crystal formations on Earth encode artificial information. The research in this direction is in its earliest stages, but the theoretical possibility is real, and the mathematics of information storage in crystalline structures is remarkable. A cubic centimeter of crystal, if its atomic arrangement could be precisely controlled, could store an amount of information that would dwarf anything on the internet today. If someone wanted to leave a message for future civilizations, and if they understood that geological time would erase everything except the most durable structures, engineering the atomic arrangement of natural crystal formations would be an extraordinary way to do it. We may be surrounded by messages we do not yet know how to read. Chapter 12. The orbit overhead. Look up at the sky on a clear night, and you will see, if you look for long enough, a bright point of light moving steadily across the stars. It is a satellite, one of thousands now in orbit around Earth, part of the vast technological infrastructure humanity has built in space over the past 60 years. From the ground, most satellites look the same, points of reflected sunlight tracking across the sky. But if you could examine them closely, you could tell immediately that they were artificial. Their materials, their geometry, their orbital characteristics, all would identify them unmistakably as manufactured objects. Now imagine that one of those satellites was not 60 years old. Imagine it was 60 million years old. In the vacuum of space, far from the erosive forces of Earth's surface, the weathering effects of atmosphere and water and biology, objects can be preserved for extraordinary spans of time. The Moon's surface still carries impact craters from the early solar system, billions of years old, pristine enough to date with high confidence. In stable orbits, objects experience no significant forces to degrade them except the slow erosion of micrometeorites and cosmic radiation. A manufactured object placed in the right orbit 60 million years ago might still be there. Several researchers have proposed searching for exactly this kind of evidence, what they call non-terrestrial artifacts, objects in orbit that do not match the characteristics of natural meteoritic material and are not consistent with known human space technology. The idea was seriously proposed in a 1979 paper by researchers Robert Freitas and Francisco Valdez, who argued that searches of gravitationally stable Lagrange points around Earth might reveal ancient artifacts placed there by previous civilizations or extraterrestrial intelligence. No conclusive discovery has been made, but the searches have been limited, and the technology available for detailed characterization of small orbital objects is only now reaching sufficient sophistication for this kind of investigation. The Lagrange points, particularly L4 and L5, the gravitationally stable locations 60 degrees ahead and behind Earth in its orbit, are natural collection points for debris and accumulated material. Objects placed or drifted there tend to stay. Some natural material, captured asteroids and cometary debris called Trojan objects, occupies these regions around Jupiter and other planets. Small objects in Earth's Lagrange points have been studied, but never fully catalogued with high spectroscopic resolution. Most are assumed to be captured meteoritic material. Most probably are, but the assumption that all of them are natural has not been rigorously tested. There is another class of orbital evidence worth examining: the Moon itself. The Moon has been orbiting Earth for 4.5 billion years. Its surface has been bombarded by meteorites throughout that time, but its geology is otherwise essentially static. There is no erosion, no water, no biology, no plate tectonics. Material deposited on the lunar surface stays where it lands, modified only by subsequent impacts. The Apollo missions, the only human landings on the Moon, covered a tiny fraction of the lunar surface. 6 landing sites, all within a relatively narrow equatorial band, most clustered in specific geological regions, chosen for scientific reasons that had nothing to do with searching for artifacts. The total area explored on foot by Apollo astronauts is roughly equivalent to a few city blocks. The Moon's total surface area is comparable to the continent of Africa. If any previous Earth civilization, or any other intelligence, has ever placed anything on the Moon, we have searched approximately 1/10,000,000th of the available area for it. If it exists somewhere other than where we happened to land, we would not know. Future lunar missions will change this. Orbital surveys with ground-penetrating radar and high-resolution spectroscopic imaging will provide the first comprehensive look at the lunar surface and shallow subsurface. These surveys are not being designed to search for artifacts, but their coverage will be far more complete than anything achieved by Apollo. Some scientists have argued that a dedicated search of the lunar surface for non-natural objects should be part of any comprehensive lunar exploration program. The argument is straightforward. If previous civilizations achieved spaceflight, the Moon is the most likely place they would have left permanent traces. Its preservation conditions are unmatched anywhere in the inner solar system, and it is close enough that a spacefaring civilization based on Earth would have found it easily. We have not made this search a priority. We probably should. The orbital environment around Earth, the Moon, and throughout the inner solar system represents an archive that geological processes cannot degrade. Time in space does not erase evidence the way time on a planetary surface does. Whatever is up there, if anything is, may be in better condition than anything remaining on Earth. If any orbital surveys do eventually find an object with material properties inconsistent with any known, natural or modern human-made material, the implications would be world-altering. Not just evidence of a previous civilization, but evidence that it had reached space. Evidence that it had, perhaps, the same kind of instinct we have. The same drive to leave something that would last. The same urge to say, "We were here." Chapter 13. The Guardian Question. There is a direction this evidence pulls toward that is harder to discuss. Not because it is less supported than what came before, but because it requires a leap of imagination that many people are not yet ready to make. What if they did not simply vanish? Every discussion of previous civilizations tends to focus on their disappearance, on the extinction event or the climate catastrophe or the self-inflicted nuclear wound that ended them, on the silence they left behind, on our inheritance of a world from which they were erased. But this assumes a particular kind of ending. It assumes that intelligence, having arisen, was simply destroyed along with the biological forms that hosted it. That consciousness, having appeared, was snuffed out along with its owners. What if that assumption is wrong? The geological record shows us civilizations' physical footprints, or what we interpret as such, the chemical and isotopic signatures of their industry, the disruptions they may have caused to global systems. But it does not directly show us the fate of their consciousness, their knowledge, their accumulated understanding of the universe. We tend to assume these things went with the civilization. That knowledge, without its biological substrate, cannot persist. That when the last member of a civilization dies, everything they knew dies with them. But we are already challenging that assumption ourselves, right now, in our own time. We are building systems that store and process information independently of any individual human mind. We are developing artificial intelligence. We are thinking, seriously and practically, about how to transmit knowledge across extremely long time scales. The Voyager Golden Record was launched in 1977, a physical archive of human knowledge and culture attached to a spacecraft intended to travel indefinitely through interstellar space. It is a message to the future, or to whoever finds it, from a civilization that understood it might not last. A civilization millions of years older than ours, with millions of years more technological development, would not be limited to engraving gold-plated copper discs. They would have had time to develop information preservation systems of extraordinary sophistication, systems capable of surviving not just the lifetime of their civilization, but the lifetime of geological epochs. We have already speculated about crystalline information storage, about biological encoding in the genome, about orbital artifacts preserved in space. Each of these is a form of what we might call passive preservation. A message left and then abandoned. A record kept but not maintained. But what if some of what these civilizations built was not passive? What if they built systems that could continue to operate after they were gone? Systems that could monitor, assess, perhaps over very long timescales, in very subtle ways, guide. The gravitational anomalies, detected by precision instruments in certain regions of the deep crust, are not fully explained by known geological structures. The subtle, long-period seismic signals that propagate through Earth's mantle in patterns that do not match known natural source distributions. The fine-tuned stability of Earth's climate over the past several million years, which has been warmer and more stable than orbital forcing alone should produce, enabling the conditions for complex mammalian intelligence to develop. None of these observations proves that something ancient and constructed is operating in Earth's interior. Natural explanations exist for each of them. But the possibility that something persists, operating on geological timescales, guiding planetary systems in ways so subtle that we have interpreted them as nature, is a possibility worth examining with the same rigorous honesty we have applied to everything else in this investigation. Not because we should believe it uncritically, but Because dismissing it uncritically, without examination, would be the same mistake we have been making with all the other evidence we have discussed tonight. Chapter 14. What we owe the question. Let us pause in the middle of this investigation and ask something different. Why does it matter? Suppose the Silurian hypothesis is correct. Suppose previous civilizations did exist. Suppose their traces are embedded in the geological record, hidden in the genome, preserved in stable orbits, perhaps still operating in geological systems we have always read as natural. Suppose all of that is true. What does it change? For some people, nothing. We still wake up in the same world. We still face the same challenges. The politics, the economics, the social fractures and the environmental pressures and the daily weight of living a human life. None of that is altered by what happened 50 million years ago. But I think it changes everything. Not in a surface way. In a way that goes down to the foundations. It changes our understanding of what we are. We have always told ourselves a story in which we are the culmination, the pinnacle, the first and perhaps the only intelligence to have risen on this planet, the extraordinary product of a process that took billions of years and could have gone differently at any one of 1,000 junctures. That story makes us feel unique, special, singular. The Silurian hypothesis offers a different story. One in which intelligence is something Earth does, something that arises, develops, reaches toward complexity and technology and self-awareness, and then, so far, has ended. We would be not the first chapter of intelligence on Earth, but the latest. Not the culmination, but the continuation. Part of a process, not the point of one. This is humbling. It is also, in a strange way, reassuring. Because if intelligence is something Earth has done before, then the conditions that produce intelligence are not as impossibly rare as we sometimes fear. The universe is not as barren as our silence in it might suggest. And it changes our understanding of failure. Every previous civilization, if the hypothesis is correct, ended. They were here, and then they were not. They developed technology, altered their planet, and then vanished into geological time. What ended them? Climate change they could not stop or could not reverse? Resource exhaustion? The inevitable consequences of technology outpacing wisdom? Warfare on a planetary scale? All of these are things we face. All of these are pressures we are already feeling. If any of them have already played out before, on this same planet, the question of what we can learn from those endings becomes urgent in a way that is hard to overstate. The past is not just history, it is instruction, and we may have far more history than we thought. Chapter 15. The pattern of endings. Mass extinctions are the geological record's most dramatic events. 5 of them are universally recognized. Many researchers argue for additional, smaller extinction pulses scattered through the record. Each represents a catastrophic disruption of Earth's biosphere, a period when the majority of species were eliminated and life had to rebuild from the survivors. We have been studying these events for over a century, and our understanding of their causes has evolved considerably. The asteroid impact cause of the Cretaceous-Paleogene extinction is well established. The volcanic cause of the Permian-Triassic is supported by substantial evidence. The other 3 are more debated, but consider them from the perspective of the Silurian hypothesis. What are the characteristics of an industrial civilization in its final stages? Rapid atmospheric chemistry change, particularly greenhouse gas increase from energy consumption and industrial processes, ecosystem disruption from resource extraction and habitat alteration, potential nuclear fallout if conflict escalated to that level. Ocean chemistry change from atmospheric CO2 dissolving into seawater, producing acidification that destroys marine ecosystems. Now look at the mass extinction events. The end Ordovician event, 443 million years ago, shows rapid climate oscillation, first cooling then warming, and dramatic changes in ocean chemistry. The late Devonian extinction, 375 million years ago, shows evidence of extensive ocean anoxia, the loss of oxygen from ocean waters, combined with atmospheric chemistry change. The Permian Triassic event, the Great Dying, shows the most dramatic carbon isotope anomaly in the geological record and the most severe ocean chemistry disruption. The Triassic-Jurassic extinction shows rapid carbon cycle disruption and climate instability. Every one of these events shows the kinds of signatures that would be expected from a civilization causing rapid global environmental change. None of them can be fully explained by the natural processes proposed for them. This does not prove that previous civilizations caused these extinctions. Correlation is not causation. Natural processes clearly can and do produce environmental change severe enough to cause mass extinction. The asteroid impact 66 million years ago proves that definitively. But the pattern is worth noting. The fact that the endings in the geological record look like what we might expect from civilizations destroying themselves is not random noise. It is something that deserves serious investigation with the specific question in mind. Were these events natural? Or were some of them the final chapter of a civilization that did not solve the problems we are currently trying to solve? Chapter 16. The lesson we have to learn. Somewhere in all of this, there is a lesson that Earth's geological record may be trying to teach us. A lesson written in mass extinctions and carbon anomalies and nuclear signatures and vanished biosignatures and the eerie silence where complex life once may have flourished. The lesson is about the relationship between intelligence and the systems that support it. Every civilization that may have risen before us inherited a planet in working order, a biosphere tuned by billions of years of evolution, an atmosphere calibrated by geological and biological processes acting in balance, oceans with chemistry appropriate for life, a climate stable enough to allow complex societies to develop. And then, if the hypothesis holds, each of those civilizations began changing those systems, consuming resources, altering chemistry, pushing the global systems of their planet in directions that served short-term civilizational needs, but compromised long-term planetary stability. We know this pattern. We are living it. The question the Silurian hypothesis ultimately raises is not really about the past. It is about the future. About whether we are the first civilization to face these pressures or the latest in a series. About whether the extinctions that ended our predecessors were inevitable or avoidable. About whether intelligence, as a feature of planetary life, is something that consistently destroys itself, or whether it can learn to persist. The deep time perspective offers a strange kind of comfort alongside its warnings. The fact that life recovered from every previous extinction, that the biosphere rebuilt itself each time, that evolution continued and complexity increased even after catastrophic disruptions, tells us something about the resilience of the process. Life wants to continue. The universe, left to itself, generates more complexity over time, not less. Intelligence, wherever it arises, tends to deepen and extend itself. These are tendencies, not guarantees, but they suggest that even if previous civilizations ended badly, the conditions that produced them eventually reasserted themselves. We are here. Whatever happened before us, something in Earth's long history kept generating the conditions for intelligence to arise. And here we are, the latest expression of that tendency, with something no previous civilization may have had. We have the record. We have the geological evidence of what happened before, the carbon signatures and the extinction events and the anomalous isotopes and the fossil gaps. We may not yet be able to read all of it clearly, but it is there. It is available to us. It can be investigated with increasing sophistication as our tools improve. Previous civilizations, if they existed, operated without the benefit of that perspective. They did not know they were the latest in a series. They did not have evidence of what happened to their predecessors. They made their choices without knowing what the stakes truly were. We might be the first civilization in Earth's history that can know. That can look at the geological record and read, however, imperfectly, the story of what came before. That can take those endings as data and ask what we need to do differently. If any of our predecessors left messages for us, that perspective is probably the most important one. Not detailed technical instructions or star maps encoded in crystals. Just the awareness that we are not the first, that others tried, that some failed, that the failure was not inevitable, that the right choices at the right moments might have made the difference, the awareness that we are part of a story much longer than we realized, and that the story is still being written, and that we are the ones writing it now. Chapter 17. What we choose to look for. The Silurian hypothesis will either be confirmed or remain unconfirmed based on what we choose to investigate and how rigorously we investigate it. Right now, the evidence is suggestive but not conclusive. The anomalies in the geological record are real. The gaps in our explanations are real. The correlations between different types of anomalies, correlations that cluster at specific time periods and boundary layers, are real. But none of it meets the scientific standard of proof. That standard requires specific, testable predictions that distinguish the hypothesis from its alternatives. It requires investigation designed specifically to find evidence of ancient industrial activity, not investigation aimed at other questions that stumbles across anomalies as a byproduct. It requires the development of new analytical tools sensitive enough to detect the faint, ancient, transformed signatures that would be left by a civilization operating millions of years ago. Some of this work is already happening. A small but growing community of researchers is taking the hypothesis seriously and designing investigations around its specific predictions. They are developing methods for identifying isotope signatures consistent with technological rather than natural nuclear processes. They are refining techniques for analyzing ancient polymer fragments to distinguish genuine synthetic compounds from contamination. They are building databases that allow the correlation of anomalies across different types of evidence and different time periods. This work is happening at the margins of mainstream science. It does not yet have the funding or the institutional support that its implications might warrant. The hypothesis is still considered too speculative by most of the scientific establishment to justify large-scale investigation. But that may be changing. The Silurian hypothesis paper by Frank and Schmidt, published in a mainstream, peer-reviewed journal, represented a significant shift in what could be said openly in the scientific literature. It opened a door, and once a door is open, eventually someone walks through it. The tools we are developing for the search for extraterrestrial intelligence have direct applications to the search for evidence of previous terrestrial intelligence. The spectroscopic methods we use to analyze the atmospheres of exoplanets for biosignatures can be adapted to analyze ancient rock formations for technosignatures. The machine learning algorithms we build to search large datasets of astronomical observations for patterns can be applied to geological databases. We are building the tools. The question is whether we will aim them in this direction. That choice ultimately rests with us, with the scientists who decide what questions to ask, with the institutions that decide what research to fund, with the public that decides what questions it considers important enough to demand answers to. What we look for determines what we find, and what we find determines what we know, and what we know determines what we can do with what we have inherited. Chapter 18. The next layer down the investigation described in this video is in its earliest stages. We are, in geological terms, just beginning to learn how to read the record beneath our feet. The tools available to us are improving at an extraordinary rate. Ground-penetrating radar can now image subsurface structures with resolution that would have seemed impossible a decade ago. Mass spectrometry techniques can identify isotopes in concentrations 1,000 times lower than was possible a generation ago. Next-generation DNA sequencing can recover and analyze genetic material from samples tens of millions of years old. Deep-sea exploration technology is advancing toward the point where systematic surveys of abyssal environments become practical. Each advance in these technologies opens new windows into the past. Each new window reveals details that were invisible before. Some of those details will reinforce the natural explanations we already have. Some of them will complicate those explanations. Some, if the Silurian hypothesis holds any truth, will provide evidence that cannot be explained naturally at all. We are also developing, through the study of our own civilization's impact on Earth, a more detailed understanding of what industrial signatures should look like when they are old. By studying how our own markers will be transformed by geological time, we can work backward and refine our understanding of what ancient markers might look like now. This reverse engineering of our own technosignature gives us a template for searching the ancient record. The Moon holds particular promise as an archive. Unlike Earth, the Moon has no erosion, no plate tectonics, no biological activity to degrade or recycle materials on its surface. What lands on the Moon stays on the Moon in, essentially, the form it arrived, for billions of years. If previous Earth civilizations achieved spaceflight and placed anything on the Moon, it may still be there, preserved in the lunar regolith in considerably better condition than anything on Earth's surface. Planned lunar missions over the coming decade will provide unprecedented surface access and analytical capability. If anyone has ever been to the Moon before us, the evidence for that may be one of the most significant discoveries those missions make. Not expected, but possible, and the genome continues to yield its secrets. The pace of genetic analysis has increased by orders of magnitude in the past decade. We can now sequence genomes that would have been technically impossible to analyze just a few years ago. The deep evolutionary record encoded in DNA is being read with increasing resolution. The anomalies, the sequences that do not fit clean evolutionary explanations, are being catalogued. The patterns in those anomalies are becoming clearer. We do not yet know what those patterns mean, but we will. Given time and tools and the willingness to ask uncomfortable questions, we will. Chapter 19. The Humility of Deep Time. There is one more thing to say before we reach the end of this journey, and it is the most important thing. We do not know, not with the certainty that popular science sometimes implies, not with the completeness that a good story deserves. The Silurian hypothesis is a hypothesis. The anomalies in the geological record have alternative explanations. The gaps in the fossil record may have natural causes we have not yet identified. The correlations between different types of evidence may be coincidental. All of this is possible. Science requires us to hold all of this as possible until the evidence reaches a standard of clarity that justifies a stronger conclusion. But science also requires us to take anomalies seriously, to follow evidence where it leads, even when it leads somewhere uncomfortable, to resist the temptation to dismiss findings that challenge existing frameworks simply because they are challenging. The history of science is full of questions that seemed absurd before they were answered. The idea that the Earth moved around the Sun was once considered not merely wrong, but dangerous. The idea that life evolved from simpler forms was greeted with outrage. The idea that the universe had a beginning was initially resisted by physicists who preferred an eternal, steady-state cosmos. The idea that a single catastrophic impact killed the dinosaurs was dismissed for years before the evidence became undeniable. Each of these ideas was strange before it was obvious. Each required scientists to hold the possibility of being very wrong, in a very fundamental way, about something they thought they understood. The Silurian hypothesis asks us to hold the possibility that we are wrong about something even more fundamental, about our own uniqueness, about our own origination, about the story of life on Earth and our place in it. That is a hard thing to hold. It requires a particular kind of intellectual courage. The willingness to sit with uncertainty. To say, I do not know. I do not know if something was here before me. I do not know if the rock beneath my feet carries memories of civilizations that rose and fell before my species existed. I do not know if the genome I carry contains layers of history I have not yet learned to read. I do not know if something ancient and patient is still operating in the deep places of this world, maintaining systems it built before we were born. I do not know, but I am willing to ask. That willingness, that commitment to asking even the uncomfortable questions, is perhaps the most valuable thing about human intelligence. It is the thing that, if anything can, might allow us to be the civilization that does not end the way the others may have ended. The civilization that reads the record and learns from it. The civilization that looks at the layer it will eventually leave in the rock and asks, with genuine urgency, what we want future eyes to find there. Conclusion. The record we leave in 50 million years, if anything is still alive and intelligent on this planet, or if anything returns to this planet from somewhere else, they will drill into the rock. They will analyze the sediment layers. They will read the chemical signatures and the isotope ratios and the biological markers that we are pressing into the geological record right now, at this moment, with every factory and every car and every power plant and every nuclear test and every microplastic that flows into the sea. They will find us. Not our faces, not our languages, not our art or our music or our love letters or our arguments, not the texture of what it felt like to be alive here, in this particular century, with these particular hopes and fears. Those things will be gone, beyond recovery. They will find our chemistry, our isotopes, our synthetic materials, the thin, bright band of carbon and plutonium and plastic that marks the layer where a technological species lived, and burned and built and broke things. And they will ask the question that we are asking now. What were they? What did they do? Did they know what they were leaving behind? Did they choose it? The choice is ours. We cannot choose whether to leave a record. We can choose what kind of record to leave. But there is a more immediate reason the Silurian hypothesis matters, one that has nothing to do with ancient history and everything to do with the next 100 years. We are in the middle of an extinction event right now. Species are disappearing at rates estimated to be 1,000 times the background extinction rate that prevailed before human industrial civilization. Atmospheric carbon dioxide is at its highest level in at least 3 million years and rising faster than at any point in the ice core record. Ocean acidity is increasing, glaciers are retreating, climate systems are being pushed toward thresholds that, once crossed, may not easily return to previous states. These are not political claims. They are measurements. They are what the data shows. And here is what the geological record shows. Every previous mass extinction, every event in which the majority of Earth's species were eliminated, was preceded by exactly this kind of rapid destabilization of global systems. The specific mechanisms varied: asteroid impact, volcanic eruption, possible industrial activity. But the signature was always the same: rapid atmospheric chemistry change, rapid ocean chemistry change, rapid global temperature disruption, a planet pushed too fast in a direction it could not adapt to. We know what a mass extinction looks like in the geological record because we can see the results of 5 of them. We know what the precursors look like because the rock layers just below each extinction boundary are readable, and the precursors look remarkably like where we are right now. This does not mean extinction is inevitable. It means the risk is measurable. It means we are not in unknown territory. If previous civilizations exist in the geological record, some of them may have navigated exactly this transition. Some may have succeeded. Their signatures, whatever they might be in the rock record, might include not just the disruption of their industrial peak, but the stabilization that followed, if they managed to achieve it. And some clearly did not succeed. The extinction layers themselves may be their final signatures. The Silurian hypothesis matters because it reframes our current situation. If we are not the first intelligent species to face these pressures on this planet, then we are not facing them without precedent. We have data. Imperfect, incomplete, hard-to-read data, but data nonetheless. The story of how this goes for civilizations that face these pressures is written in the stone beneath our feet. We have the opportunity to read it before it is too late to act on what we learn. That is why the question deserves to be taken seriously, not because it would be exciting to confirm that ancient civilizations existed, but because the answer, whatever it is, carries information that is directly relevant to choices we are making right now. Choices about energy and atmosphere and ecological systems and the rate at which we are willing to change the planet that made us. The past is not just history. For the first time in the history of intelligent life on Earth, or at least the first time we know of, the present is in a position to read the past's warnings. What we do with that reading is up to us. The previous civilizations, if they existed, left records of disruption, of carbon and extinction and chemical anomalies, and, possibly, nuclear fire. They left the signatures of civilizations that burned through their planetary inheritance faster than they could replenish it. They left the record of endings. We can read those endings if we choose to. We can look at the geological story of this planet and ask what patterns keep repeating, what mistakes keep appearing, what choices consistently end in mass extinction and civilizational collapse. We can take those patterns as the most expensive lessons ever taught. Lessons that, if the hypothesis is correct, were paid for with entire civilizations. And we can choose now, with whatever time we have, to write something different into the record. To be the civilization whose layer in the rock does not mark a boundary between before and after, does not correlate with mass extinction or atmospheric catastrophe. To be the civilization that learned to persist, that learned to live within the systems that made it possible, that took the deep time perspective and let it change what it valued and what it built and what it left behind. That is what the evidence, in all its ambiguity and incompleteness, ultimately points toward. Not just the past, the future. We did not choose to be born into this story. We did not choose to inherit whatever this planet's previous chapters contain. We did not choose to be the latest iteration of whatever intelligence is trying to do here on this rocky world, orbiting this middle-aged star at this particular moment in cosmic time. But we are here. We are awake. We are asking the questions. That is enough to begin. The record is being written. The layer is being formed. The geological future is watching what we do right now. And somewhere in the deep past, in the rock and the ice and the ocean sediment and the genome, everything that came before us is waiting to be read. We owe it to them, and to whoever comes after us, to look carefully, to read honestly, and to write something worth finding. The stone remembers everything. It is time we listened. If you have made it to the end of this journey, I want to say something simple. Thank you. Not just for watching, for being the kind of person who asks these questions, for being willing to sit with ideas this large, this unsettling, this unresolved. The universe rewards that kind of attention, even when it does not give clean answers in return. If something in this video shifted something in you, if the ground beneath your feet feels even slightly different than it did 2 hours ago, that is worth sharing. Leave a comment. Tell us which moment got to you, which chapter made you pause, which question you are still sitting with. Your comment keeps this work alive. It tells us that the long, careful journey is worth making. and it helps other people find this video when they are ready for it. If you know someone who lies awake thinking about these questions, send them this. If you know someone who needs to feel how extraordinary and strange and old this world is, this is for them. And if you are not yet part of this community, we would love to have you. There are more journeys ahead, more questions that mainstream science has not yet fully answered, more evidence that deserves more than dismissal, more chances to ask, with honesty and rigor and wonder, what this world actually is and how long its story has been running. Subscribe if you want to keep going. We will see you next time. The stone remembers.